Welcome to my class 12 Physics, chapter that is Alternating Current, and in this class we will discuss about LCR series circuit and impedance. And before that, you know about R circuit, L circuit and the C circuit. R is the symbol of the resistance, L is the symbol for inductance, and the C for capacitance. R circuit means we write that is AC voltage applied to a resistor only. Only a resistor is there. If only a resistor is there, if only a single resistor is there, that is known as the R circuit. Clear? And here AC voltage means that is the applied AC voltage. For applied AC voltage, we write the symbol V. V is equal to V0 sin omega t, and here V means that is the instantaneous value of AC voltage. V0, that is the peak value or maximum value of the AC voltage, and here omega t is the phase of the AC voltage. And for R circuit, you know the expression for the instantaneous current. For that we write I is equal to I0 sin omega t, and here also I is the symbol for instantaneous alternating current, and I0 means that is the maximum value or that is the peak value, and omega t, here omega t is also known as the phase of the current. And look at the equation. V, in case of V means applied voltage. In case of applied voltage, here phase is omega t, and in case of current, here also phase is omega t. That means both are in same phase. Both are in same phase. Then what is the phase difference? We write phase difference between voltage and current. We write that symbol is phi. Phi is equal to omega t minus omega t, that is equal to 0. And phi is known as the phase difference. Phi is known as the phase difference. That means suppose we take the current phasor. Suppose this one is the current phasor. This one is the current phasor. For current phasor we write suppose I, and this is also voltage phasor. This is also voltage phasor. For voltage phasor, here we write VR. R means that is the R circuit or resistor circuit. That means here current phasor and voltage phasor both are in the same direction. Why? Because phase difference between voltage and current, that is 0. That is 0 means both are in same phase. In case of R circuit, your voltage and current both are in same phase. Same phase means phase difference is 0. Phase difference is 0 means current phasor and voltage phasor both are in the same direction. Clear? And here from Ohm's law, we write V is equal to IR. You know that is Ohm's law. And here V is the applied voltage, and your circuit is R circuit. So that in place of V, simply we write VR. Clear? And here R is the resistance, and you know the meaning of resistance. Resistance means simply opposition of what to the flow of current by a resistor. That is known as the R. R is the resistance. Clear? Similarly, in case of L circuit, we write AC voltage applied to one inductor only. And an inductor means that may be your coil or your choke. These are known as the inductor, examples of inductor. And just like this is the symbol of inductor. Clear? And in case of inductor circuit or L circuit, L for inductance, AC circuit applied to an inductor only. In this case, applied voltage, that is V is equal to V0 sin omega t, because applied voltage in all cases are same. In case of resistor circuit, that is V is equal to V0 sin omega t. In case of inductor circuit, that is also V is equal to V0 into omega sin omega t, and here V is the instantaneous value of the alternating voltage. Same thing, V0 is the maximum value, and omega t, that is the phase. You know that is the phase of the applied voltage. Similarly, expression for current, you know, that is I is equal to I0 sin omega t minus pi by 2. In case of AC voltage applied to an inductor only, you know the expression of current is equal to this one. If we compare the phase, this is the phase of the applied voltage, and this is the phase of the current flowing through the circuit. Current means that is the alternating current. And what is the difference of phase? For difference of phase, we write the symbol phi. Phi is equal to phase difference. And for phase difference, we write that is phase of the AC voltage, we write that is omega t, minus phase of the current, that is omega t minus pi by 2. Clear? And we write that is omega t minus omega t plus pi by 2, and omega t cancel. Only remaining is equal to pi by 2. That means AC voltage applied to an inductor only, or simply we write L circuit. In case of L circuit, phase difference is equal to pi by 2. If we compare the phase of voltage and current, in case of current, here phase is omega t minus pi by 2, not plus pi by 2. Minus pi by 2 means that is lags behind. Plus pi by 2 means we write that is ahead. You also know that. That means here we write this is the current, simply we write current lags behind to the voltage by a pi by 2 radian, or by a phase of pi by 2 radian. Simply we write current lags behind means a minus sign is there. Minus means that is the lags behind, plus means that is the ahead. Clear? So that we write current lags behind to the voltage by a phase pi by 2 radian. Lags behind means that is in the clockwise direction, and ahead means that is the anti-clockwise direction. You also know that. That means simply we also write, suppose we take the voltage phasor. Suppose this one is the voltage phasor. And here for voltage phasor we write that is VL. L means circuit is inductor only. For inductor circuit, we write symbol is L, because L for inductance. And here for current phasor, current lags behind means in the clockwise direction. So that we draw the current phasor. This one is the current phasor. For current phasor we write I, and this angle is pi by 2. That means current phasor lags behind to the voltage phasor by angle pi by 2 radian. Clear? And here also we applied Ohm's law. We write Ohm's law, that is V is equal to IR. Here we write V. In place of V, we write VL is equal to I the current flowing in the circuit, multiplied by R. Here circuit is resistor, so that we write R. But here circuit is inductor, and in case of inductor, or in case of L circuit, opposition offered to the flow of the current by an inductor, that is known as the XL. So that in place of R, we write simply XL. That means XL. XL plays the same role as compared to the resistor. In case of resistor circuit, here we write R. In case of inductor circuit, we write that is XL. Here R means that is the resistance of the resistor. Here XL means that is the inductive reactance. XL means that is inductive reactance of inductor. Inductive reactance means that is the opposition of what? To the flow of a current by an inductor only. Clear? Similarly, you also know the C circuit. For C circuit, C for capacitance, we write that is AC voltage applied to a capacitor only. Clear? And this is the symbol of a capacitor. Here only a single capacitor is there. And in case of C circuit, here also same thing, applied voltage. For applied voltage we write that is V. For applied voltage we write that is V, and V is equal to V0 sin omega t. Same thing in all cases. Here V is the instantaneous value of the AC voltage. V0 that is the maximum value or peak value. Here omega t that is the phase. Similarly, in case of C circuit, you know the expression of current. For current, you know that is I0 sin omega t plus pi by 2. In this case, that is plus pi by 2, not minus pi by 2. And you know, plus means that is ahead, minus means that is the lags behind. So that if we compare the phase of the voltage and phase of the current, the phase difference we write that is phi is equal to omega t minus omega t plus pi by 2. That implies we write phi is equal to omega t minus of pi by 2. Omega t cancel. Simply we write that is minus of pi by 2. Clear? That means simply we write here phase of current that is omega t plus pi by 2. Plus pi by 2 means that is ahead, you know that. So that we write current ahead, or we also write that is leads. Current leads the voltage. Current leads the voltage by an phase pi by 2 radian. Clear? And the leads means that is the anti-clockwise direction. So that suppose this is the voltage phasor. For voltage phasor we write that is Vc. For voltage phasor here we write Vc. C for that is the circuit is capacitor only. And for current phasor we draw the current phasor. This one is the current phasor. For current phasor we write I, and this is the phase difference. This is the phase difference between the voltage phasor and current phasor. We write that is pi by 2. That means this is the voltage phasor, and current phasor leads an angle pi by 2. Leads an angle means anti-clockwise. This is the anti-clockwise direction. Here this is the clockwise direction. Current lags behind means clockwise. Here current leads means anti-clockwise, and in all the cases this is the direction of the current, this is also direction of the current, this is also direction of the current, because you know in case of a series circuit direction of current always remains same. So that finally we write that is LCR series circuit. LCR series circuit. Here all are connected in series, not in parallel. That means current flowing through the inductor, capacitor and resistor all are same. And you draw the diagram of the LCR series circuit. These are the external wires. And you draw the circuit just like this. And this is the resistor. This is the symbol of a inductor, and a capacitor is also there. And this is the symbol of a capacitor. Clear? And we draw the external wires. These are the external wires. And we close the circuit. And here a AC voltage is applied. And this is the symbol of a AC voltage. And the applied voltage we write that is V. V is equal to V0 sin omega t. You know that. Clear? And for resistor, we write, suppose symbol is equal to R. For inductor, we write inductance, its symbol is equal to L. For capacitor, its capacitance, we write the symbol that is C. And suppose we take 2 points, that means resistor is connected between these 2 points, so that potential difference between this point and this point, we write that is VR. Similarly, inductor is connected between these 2 points, so that potential difference between this point and this point, we write that is VL, because here a inductor is connected. Similarly, for capacitor, here also we take 2 points, and the potential difference between this point and this point, we write that is Vc. And here net potential difference or applied voltage, that is V. And what is VR? You know that is VR. VR is equal to I into R. What is VL? You know that is I into XL. XL means that is the inductive reactance. And what is VC? We write VC, that is I into XC. XC means that is the capacitive reactance. XC, capacitive reactance. XL, inductive reactance. And R means that is the resistance. Clear? You know that. And now you draw the direction of the current. Suppose in case of resistor circuit, current flowing suppose in this direction. This is the direction of the current. We write that is I. And current flowing through the inductor, that is also same. This is the direction of the current flowing through the inductor. And current flowing through the capacitor, we write that is I. And this is also direction of the current, because current flowing in same direction in case of R, L and C. And when now we draw the phasor. We draw the phasor of voltage, here VR, here VL, here VC. First we draw the VR. VR is in the same direction of I. VR is in the same direction of I. So that this is the VR phasor. We write that is VR. Clear? For inductor circuit, this is the direction, this is the voltage phasor. We draw the voltage phasor. This one is the VL phasor. Similarly, for the capacitor circuit, this one is the VC phasor, voltage phasor. This one is the VC phasor. Clear? Here the both are in the same direction. Here phase difference, that is pi by 2. Here also phase difference, that is pi by 2. Clear? And V is the applied voltage. Now we will derive the expression. For current. Now you draw the phasor diagram for LCR series. This is the circuit diagram. This one is the circuit diagram. We write this one is the circuit diagram. This one is the circuit diagram. This one is the circuit diagram of a LCR series circuit. I draw the phasor diagram of the LCR series circuit. We draw the phasor diagram. Draw the phasor diagram of the LCR series circuit. Suppose here you take two axes just like this. This one is the one axis. We draw another axis. And suppose this point is the origin. For origin we write suppose that is O. Clear? And here we take three conditions. Three condition means this is the circuit diagram. Here VL and VC is there. Suppose we take maybe VL is equal to VC, maybe VL is greater than VC, maybe VL is less than VC. Clear? Suppose VL is greater than VC. This is the first condition. Suppose you take potential difference between these 2 points, that is VL, is greater than potential difference between these 2 points, that is VC. Suppose VL is greater than VC, and for this we will calculate the current. Current means alternating current, expression of the alternating current flowing through the circuit. So that is the case 1. This is the first case, VL is greater than VC. And for this we draw the phasor diagram. We draw the phasor diagram for case 1. Case 1 is VL is greater than VC. Clear? And we draw the first phasor of the VR. Suppose this one is the VR phasor. We write that is VR. Next is VL. And look at the diagram. This is the VR and VL. This is the VR phasor. This one is the VL phasor. That means the VL phasor is an angle pi by 2 with respect to the VR. VL, this is the VL. This one is the VL phasor. This one is the VC phasor. This one is the VC phasor. This is a VR phasor. This is a VL and this one is VC. Here VL phasor is at an angle pi by 2 from VR. So that we draw the VL phasor. We draw the VL phasor perpendicular to VR. This is a VL phasor. We write that is the VL phasor. Similarly for VC phasor, this one is the VC phasor, this one is the VC phasor. VC phasor is just opposite to the VL phasor. VC phasor is just opposite to the VL phasor. This is the VC phasor. And here this is the condition, VL is greater than VC. VL is greater than VC. We write this is VC phasor. Clear? Now what is the resultant? That means this is one vector, this is another vector and this is another vector. Suppose here 3 vectors are there. Simply we add these 3 vectors and all our vectors are starting from a common point. First we added 2 vectors. 2 vectors means that is the VL vector and the VC vector. And these 2 vectors are both in opposite direction. These 2 vectors are in opposite direction. Opposite direction means if suppose VL is positive, then VC is negative. This one is VC. This is the magnitude of VC. So that suppose this is the magnitude of VC up to this. Suppose this is VC. Then what is this? This is VL minus VC. We draw that is this one. This one we write that is VL minus VC. Clear? Now this is the resultant. This is the resultant of VL and VC. That is VL minus VC. Now only 2 vectors are there. One is VR, another is VL minus VC. This vector and this vector. We add these 2 vectors. Here both the vectors are starting from a common point. So that here we applied parallelogram law of vector addition. You know that. What is the parallelogram law of vector addition? You know. Suppose this is one vector. We write that is A vector. Suppose this is another vector, second vector. We write that is the B vector. And this is the angle between the 2 vectors. Suppose angle between the 2 vectors, we write that is phi. Simply we add A vector with the B vector. And its resultant, we write that is R vector. and you draw the equal vector of A vector. This is the equal vector of the B vector, and this diagonal of the parallelogram gives the resultant. We write that is R vector is equal to A vector plus B vector. Then what is the magnitude of the resultant vector? You know that is R. R is equal to A square plus B square plus twice AB cos phi and root over of this. You know this expression. This is known as the parallelogram law of vector addition. Here also same thing. We applied the parallelogram law of vector addition in this case. So that first we draw a parallelogram. First we draw a parallelogram just like this. This is parallel to VR, and with another line parallel to VL minus VC, this line. Clear? Then the resultant vector, here this one is the resultant vector, this one is the result. Result means we write that is V. Result means we write that is V. V means that is the applied voltage. V means that is applied, that is applied alternating voltage. Clear? That means VL, VR and VC. If we add VR, VC and VL, then V is the result. Clear? Then what is the phase? Phase of V, applied voltage. This is the expression. Applied voltage V is equal to V0 into sin omega t. Sin omega t, here phase of the applied voltage, that is omega t. Here also we write phase of the applied voltage, that is omega t, this angle. This angle we write that is omega t. Clear? Then look at the diagram. This is the direction of the current, means this is the current phasor, and direction of the current phasor is the same as the VR phasor. VR phasor and current phasor both are in same direction. Both are in same direction. Here also we draw the same thing. This one is the current phasor, because current phasor and VR phasor both are in the same direction. This is the current phasor. For current phasor we write that is I. Clear? And this is the angle. This is the angle between the voltage phasor and current phasor. This is the angle between voltage phasor and current phasor. We write this angle is equal to, suppose, phi, because phi is the phase difference between voltage and current. Clear? Then from this phasor diagram we write the expression of the voltage. For voltage we write simply V is equal to V0 into sin omega t. You know that. We write the expression for current I is equal to I0 into sin. What is the angle? Angle of the current. This one is the angle of the current. This angle is equal to omega t and minus this angle, that is omega t minus phi. Clear? This is the expression for applied voltage, and this is the expression for the current. Here current that is minus phi. Minus means, you know, that is the lags behind. Lags behind means this one minus pi by 2. Here minus pi by 2. Minus means that is the inductor circuit. AC circuit or AC voltage applied to an inductor only, or AC circuit containing a inductor only. Clear? That means we write here from this phasor diagram, if VL is greater than VC, this is the expression for current, and you know this expression of current is similar with the L circuit, so that this is same as or equivalent as, this is equivalent as a L circuit. That means if a LC, this is the phasor diagram of LCR series circuit. This one is the phasor diagram of LCR series circuit, and if in this case, if VL is greater than VC, then the LCR series circuit is equivalent to a L circuit, because this is same as the equation of L circuit, clear? And from this phasor diagram, we calculate the expression of voltage and also the expression of the current. We write that is from the parallelogram law of vector addition, we write V is the resultant, V is equal to, you know that is R is equal to A square plus B square plus 2AB cos phi and root over of this, here A square, here A means that is the VR, so that in place of A, we write that is VR square plus, what is B? This is the B vector means that is VL minus VC, we write that is VL minus VC and square of this, plus twice of AB, for A we write that is VR, for B we write that is VL minus VC multiplied by cos phi, phi is the angle between A vector and B vector, this one is the A vector that is VR, this one is the B vector that is VL minus VC, this angle is equal to pi by 2, so that we write multiplied by cos pi by 2, and you know the value of cos pi by 2, cos pi by 2 is equal to 0, so that this one is 0, third term that is 0, clear? So that only remaining is equal to this one, this is only remaining is equal to this one, and a root over is there. That implies we write V is equal to VR, in place of VR we write that is I into R, in place of VL we write I into XL, so that in place of a VR we write I into R and square of this, plus in place of VL we write that is I into XL, minus in place of VC we write that is I into XC whole square and root over. That implies we write V is equal to, here we write that is I square R square, plus if we take I as common, this is also I square, remaining is equal to XL minus XC square of this and root over. That implies V is equal to, we take I square as a common, I square again root over, so that is only I, we write that is I, remaining is equal to square root of R square plus XL minus X0 whole square. From this expression we write the expression of current I, the expression of the current, we take R square plus XL minus X0 whole square root over to the left hand side, so that I is equal to V divided by square root of R square plus this one is XL minus XC, clear? And this is the expression of the current. This is the expression of the current flowing through a LCR series circuit, and the condition is VL is greater than VC, clear? And we compare with the Ohm's law, you know the Ohm's law, that is V is equal to I into R, that implies I is equal to V by R, this is Ohm's law, you know that. And here also we write I is equal to V divided by this one, here I is there, in left hand side here also I is there, in right hand side here V is the applied voltage, here also V is the applied voltage. And in case of resistor circuit, here R means that is the opposition effort to the flow of current by a single resistor, and here in place of R this one is there, so that this one is the opposition effort to the flow of a current by a series LCR circuit, and this opposition effort that is known as the simply we write impedance, so that this is the expression of impedance. This is the expression of impedance, clear? Impedance means we write that is impedance. For impedance we write symbol that is Z. For impedance we write the symbol Z, that is same thing. Z means that is the opposition effort to the flow of current by a LCR series circuit. Clear? This is the definition. This one is the definition of the impedance. Then what is the mathematical expression of impedance? We write that is Z. Z is equal to this one, R square plus XL minus X0 whole square, R square plus XL minus XC square of this and root over. Clear? And this is the expression of the impedance in case of a series LCR circuit, and this one is the expression of the current in case of series LCR circuit, but condition is this one. Condition is VL is greater than VC. Clear? And from this phasor diagram here, this one is looks like a triangle. This one is looks like a triangle, and we draw the triangle. Suppose this one is the one side of the triangle, and this one is the another side of the triangle, and this one is the third side of the triangle. Clear? We compare this triangle with this one. This side is the base of the triangle, and that is known as the VR phasor. VR means circuit containing resistor only, and for this here we write, suppose that is resistance R. Clear? Similarly, this side is the same as this one. This one is VL minus VC. VL minus VC. Here we write that is in place of VL we write XL minus in place of VC we write that is XC. And the third one, this side is the resultant. Resultant means V. V means that is the applied voltage to the LCR series circuit. V means applied voltage to the LCR series circuit, and for LCR series circuit, we write that is the Z for impedance, so that this one is Z. And from this triangle means we write, suppose A, B and C. From the triangle ABC, this one is a right angle triangle, and you know, in case of the right angle triangle, you know, AB square is equal to, that is AB square plus BC square is equal to AC square. You know this expression. That implies, what is AB square? AB means we write that is R square plus BC. BC means this one. This one means we write XL minus XC whole square. AC means this one. That is Z square. That implies what is Z? We write Z is equal to root over of R square plus XL minus X0 whole square, that is equal to Z. Clear? That means from this triangle, we also derive the expression of the Z. Z means that is the impedance. So that this triangle is known as the impedance triangle. This triangle is also known as the impedance triangle. Clear? This is another impedance triangle. And this is the case 1, first case. Similarly, second case. In first case, we write that is VL is greater than VC. VL is greater than VC. Now second case is this one. VL is less than VC. We write that is case 2. VL is less than VC. VL is less than VC means this one is VL. This one is small as compared to the VC. Now for second case, we will draw the phasor diagram. For second case, we will draw the phasor diagram. We write phasor diagram. Of a series LCR circuit, and what is the condition? Condition is this one, second case, that is VL is less than VC. VL case 2, that is VL is less than VC. Clear? and you draw the phasor diagram. Same thing, we draw two axes. This one is the first axis. We draw another axis. This one is the second axis. First we draw the VR phasor. Suppose this one is the VR phasor. And another phasor, that is VL and VC. This is the VR phasor. This one is the VC. VC is perpendicular to VR, and this is VL. This one is VR phasor. This is VL. VL is perpendicular to VR, and VC. VC is also perpendicular to VR. But here VL and VC both are in the opposite direction. So that first we draw the VL phasor. First we draw the VL phasor, that is perpendicular to VR. This is the VL phasor. We write same thing. This one is the VR. This one is the VL. Next is VC. Here VC is greater than VL. We draw the VC just in the opposite direction of the VL. This one is, we write that is VC. And the magnitude of VC is greater than the VL. This is the condition. Here also three vectors are there. First vector, that is a VR. Second phasor, that is the VL. And third vector or third phasor, we write that is the VC. Because phasor means that is a rotating vector, you know that. And here we add these three vectors, and all are starting from a common point. And we write that point, that is the origin, we write that is O. And look at the figure. VL vector and VC vector both are in opposite direction. Opposite direction means one is positive and another is negative. So that this is the magnitude of a VL. Suppose this is the magnitude of a VL up to this. Suppose this is a VL, magnitude of VL. Suppose this is also the magnitude of VL. Then this is the remaining part. We write that is VC minus VL, just like the previous one. Here we write that is VL minus VC, and here we write that is the VC minus VL. We write that is VC minus VL. Clear? Now only two vectors are there. One is a VR vector, another is a VC minus VL. Both are starting from a common point. So that here also same thing. We applied the parallelogram law of vector addition. Suppose this vector is the A vector, this vector is the B vector, and you draw the parallelogram. Suppose one is same as the VR and another is same as this one, VC minus VL. Now this is the resultant vector. Here you draw the resultant vector. This one gives the resultant vector. Clear? And for resultant vector, we write that is V. For resultant vector, we write that is V. And what is the direction of current? You know the direction of current, that is same as VR. This is the current phasor. Because from this point, direction of current is same as VR. So that this is the direction of the current. And you know the expression of the applied voltage, that is V. V is equal to V0 into sine omega t. So that we write for voltage, we write this one. We write that is omega t. Clear? And this is the phase difference between the current and voltage, because this is the current phasor, this is the resultant voltage. This difference, we write that is phi. So that from this phasor diagram, we write the expression of a V. V is equal to V0 into sine, here phase is omega t, we write sine omega t. And expression for current, we write I is equal to I0 into sine. This one is the phase of current, that is omega t plus phi. We write sine omega t plus phi. Clear? If we compare these two equations here, phase of current that is omega t plus phi, plus means that is ahead, plus means phase of current leads an angle phi as compared to the phase of the voltage, leads or ahead. Ahead means you know that is the C circuit. Ahead means that is the C circuit, this one plus pi by 2, here that is phase of current that is omega t plus pi by 2. And this equation of current is similar with here also equation of current, here also omega t plus phi, and in that case that is omega t plus pi by 2, plus means ahead, so that in this case if VL is less than VC, the series LCR circuit is equivalent as a C circuit. Clear? This is equivalent as a C circuit. And from this phasor diagram, we also derive the expression of the current. Clear? And we applied the parallelogram law of a vector addition. This one is the one vector. That is VR vector. Suppose in place of VR we write that is the A vector. Suppose another vector that is the VL minus VC. In place of VC we write suppose that is the B vector. Here two vectors are there. One is A vector, another is B vector. And this one is the resultant vector. And for resultant vector we write suppose that is the R vector. Clear? Now you write R vector. For R vector we write that is V. We write simply V. V is equal to, for A vector we write that is VR. So that we write that is VR square plus B square. B square means VC minus VL. We write VC minus VL square of this plus, next is that is twice of AB. A means VR. B means that is VC minus VL multiplied by cos phi. Phi is the angle between the A vector and B vector. This angle is equal to pi by 2. And cos pi by 2 that is 0. So that third term that is tends to 0. Clear? And root over is there. Third term is 0. So that in this place we write simply 0. And the remaining is equal to this one. So that we write, that implies V is equal to, in place of VR, that is I into R square of this, plus in place of VC we write that is I into XC, in place of VL we write that is I into XL. Same thing. That implies we write V is equal to, we take I as common, so that is I square, again root over, that means simply I, remaining is equal to here R, we write that is R square, plus here remaining is XC, minus here remaining is equal to XL, square of this and root over of this. From this expression we write the expression of current I, we take this one to the left hand side, so that the expression of current that is V divided by R square plus XC minus XL square and root over of this. This is the expression of current. This is the expression of the current flowing through a LCR series circuit. And what is the condition? Condition is equal to VL minus VC. And if we compare these two expressions, here also this is the expression of current. Condition is VL is greater than VC. Here that is V divided by R square plus XL minus X0 whole square. But in this case, same expression, but here XC minus XL. Here XC minus XL, and in this case that is XL minus XC, and here square is there. So that XL minus X0 whole square, here that is XL minus XC whole square, and in this case that is XC minus XL whole square, both are same. How? Suppose you take an example. Suppose XC is equal to, we write that is 10, and XL is equal to, we write suppose that is 2. Clear? So that XC minus XL square of this, is equal to XC, that is 10, minus XL, that is 2, so that 10 minus 2, 10 minus 2 means that is 8, and square of 8, that is equal to 64. Similarly, we write, suppose XL minus XC and square of this XL is equal to 2, XC is equal to 10, so that 2 minus 10 means that is minus 8, and square of minus 8, that is also 64. That means expression for current in both the case, that is same. In case 1, that is VL is greater than VC, this one. VL is greater than VC, that means this is the expression of the current. In case 2, that is VL less than VC, this is the expression of current. And both the expression of current, that is same. Clear? Why? Because a square is there. And here also, in the second case, here also a triangle is there. This one is the triangle. This one is the triangle. And from this triangle, we also calculate the expression of the impedance. And same thing, this is the expression of current. If we compare this expression of current with Ohm's law, you know that is mathematical expression of Ohm's law, that is V is equal to IR and I is equal to V divided by R. Same thing, here left hand side I is there, here left hand side also I is there, here V, this one is V. So that here R for resistance in case of a resistor circuit, but in place of R, this one is there, so that this one plays the same role as the resistance, and this one is known as the impedance. Clear? And from this triangle, this is the triangle, from this triangle we also calculate the impedance. Same thing as the previous one, just like this. Suppose your triangle is equal to this one. We draw the triangle. This is the triangle. This one is VR, this one is VR. First we draw the VR. This one is VR. Here also we write VR. Next side, that is this side. This side is same as this side. That is VC minus VL. We draw the second side. This one. This one we write, that is VC minus VL. This is VC minus VL. This is the third side. Third side is V. We write that is the third side. Or resultant, we write that is V. Clear? So that in place of VR means that is the resistor circuit, we write simply R. VL minus VC, we write that is XC minus XL. V means we write that is the impedance Z. Clear? And this is the angle, this angle. You know this angle, here also we write that is the phi. This angle is a phi. Here also we write this angle, we write that is the phi. So that here we write from this one is a right angle triangle. This one is the right angle triangle, and we write the triangle that is A, B and C, and we write that is square of AB plus square of BC is equal to square of AC. Same thing. That implies AB is equal to R, we write that is R square, plus BC, this one is BC, we write that is XC minus XL whole square, and SC is equal to, we write that is Z square. And from this expression we write what is Z. Z is equal to square root of R square plus XC minus XL whole square and root over of this is equal to Z. And Z for impedance. This is the expression of Z. Look at this expression. R square plus XC minus XL. Same thing. R square plus XC minus XL whole square. So that this triangle is also known as the impedance triangle. Clear? This is the case 2. And the next case, third case, this one. VL is equal to VC. This is the third case. We write that is case third. Here also we draw the phasor diagram. VL is equal to VC, both are same. We draw the phasor diagram. phasor diagram. What is the condition? Condition that is VL is equal to VC. Clear? And same thing. Suppose this one is the one axis and this one is the another axis and this point is the origin, and we draw the first VR phasor. Suppose this is the VR phasor and VL is equal to VC. This is the VL phasor and this one is the VC phasor. We write this is VR phasor, this is VL phasor. We write that is the VL phasor and this is the VC phasor. Here both are same. Magnitude of VC is equal to magnitude of VL. So that VL and VC both are same. So that if we add VL with VC, result is 0. Result is 0. Only remaining is equal to VR. Only remaining is equal to VR. So that VR is equal to V. This is the result. VR is equal to V. And we draw the current phasor. And you know, direction of current phasor is same as the VR. This is the current phasor. For current phasor we write I. Clear? And for the resultant V, you know the expression that is V is equal to V0 into sine omega t. That means phase is omega t. This is the phase. This is the phase of the applied voltage. We write omega t. And this is also same as the phase of current. That is omega t. So that we write the expression of current. That is I is equal to I0 into sine omega t. Here both are in the same phase. Both are in the same phase means that is equivalent to a AC circuit containing only resistor. So that finally we get case 1. First case, look at the figure. First case, VL is greater than VC. VL is greater than VC. This is the expression of current. We write the expression of current. First case, that is VL is greater than VC. And expression of current, we write that is I. I is equal to V divided by R square plus, look at the expression. This one is the expression XL minus XC. We write that is XL minus XC square of this and root over of this. This is the expression of the current. Similarly for the second case, that is VL is less than VC. For this, you know the expression of current, that is I is equal to V divided by R square plus, for second case, this one is the expression of current, that is XC minus XL. We write that is XC minus XL square of this and the root over of this. Clear? Similarly for the third case, we write that is VL is equal to VC. Here expression of current, we write that is I is equal to V divided by this one. Here we write the expression, both are in the same page. So that here if we applied the parallelogram law vector addition, only remaining is equal to V, and V is equal to VR. Here V is the same as VR. Then what is VR? You know the expression for VR. VR is equal to, that is I multiplied by R. You know the expression. That implies what is the expression of current? I is equal to, we write that is VR divided by R, or we write in place of VR that is V, because both are same. V is equal to R. Or from this expression also, if XC is equal to XL, if VC is equal to VL, then automatically XC is equal to XL. So that if XC is equal to XL, then this one is equal to 0. Only remaining is equal to R square, and root over of R square, that is equal to R. So that I is equal to V by R. So that your equation is equal to this one. That means finally we get, if VL is greater than VC, if VL is greater than VC, in this case, you also know the equation of the current, this one. Equation of the current, this one. I0 sin omega t minus pi. Condition is VL is greater than VC. VL is greater than VC. Expression for current, that is I0 sin omega t minus pi. Expression of current, we write that is I0 sin omega t minus pi. Minus pi means, you know, that is the lags behind. Lags behind means, you know, that is the L circuit, that means AC circuit containing only inductor. That means finally we get, if VL is greater than VC, then the LCR series circuit is equivalent to AC circuit containing inductor only, or we write that is L circuit. We write that is simply L circuit, or we write that is equivalent to AC circuit containing inductor only. Clear? This is the first case. Similarly, second case, VL is less than VC. In this case also, this is the expression of the current. VL is less than VC, that is expression for current I0 sin omega t plus phi. We write same thing, that is I0 sin omega t plus phi. Plus means that is leads means, you know, that is the C circuit. C circuit means, in this case, the LCR series circuit is equivalent to AC circuit containing capacitor only. Clear? Capacitor only. This is the second case. Similarly, this one is the third case. And in third case, this one, current and voltage both are in the same direction. Same direction means same phase. Same phase means that is the R circuit. Same phase means that is the R circuit. Here you write the expression of current is equal to, that is I0 into sin omega t. Sin omega t means the LCR series circuit is equivalent to AC circuit containing resistor only. Clear? And in this case, expression of the current gives the maximum value. This is the maximum value of the current, because here R square plus XL minus XC, one extra term is there. Here also one extra term is there. Here only R is there. So that this expression of current gives the maximum value. Maximum value means that is the resonance condition. Resonance condition means, here we write that is VL is equal to VC, or we write that is XL is equal to XC. That means if XL is equal to XC, XL means that is the inductive reactance. XC means that is the capacitive reactance. That means in case of a LCR series circuit, if inductive reactance is equal to capacitive reactance, we get the maximum current. And that is the resonance condition. Clear? And this is all about your LCR series circuit and impedance. And in the next class, we will discuss about resonance condition in case of a LCR series circuit. Thank you.